In other lessons, we used what were called our sum and difference identities or formulas that we could use to find the sum, the sign for the sum of two angles or the difference of two angles. In this lesson, we want to look at how to find our double angles. And so we're wanting to know things along the line of what the sine of twice an angle is, 2 theta. Well, we know that 2 theta is the same as theta plus theta. So we can use our sum formula. This is the sine of the first, cosine of the second, plus cosine of the first, sine of the second. Well, since these are the same because of the commutative property, sine times cosine, then what we have is 2 sine theta cosine theta. And this is our double angle for the sine of 2 theta. And I'm just going to put that over here. So the sine of 2 theta, or twice any angle, is equal to 2 times the sine of the angle times the cosine of the angle. And in just a little bit we'll see how we can use that. Well, let's do the same thing for the cosine of 2 theta. That would be the cosine of theta plus theta. So it's the cosine of the first, cosine of the second, minus sine of the first, sine of the second. So what we end up with is cosine squared theta minus sine squared theta. And that's our double angle for the cosine. Now, because those were squared, we could substitute in from our Pythagorean identities, and we could get some variations of these. So we could say, well, the cosine squared minus, and for sine squared, we could substitute in 1 minus cosine squared, which gives us cosine squared theta minus 1 plus cosine squared theta, which would be 2 cosine squared theta minus 1. And now we have it in terms of just one function. So there's a variation for this. It could also be 2 cosine squared theta minus 1, in case you were just given the cosine. But we could, instead of having substituted in for sine squared, we could have substituted in for cosine squared. And we know that cosine squared is equal to 1 minus sine squared minus sine squared. So removing our parentheses, then we have 1 minus 2 sine squared. So this way, if we have a choice of which function to use based upon what we were given. So it could also be 1 minus 2 sine squared theta. And then the last one we want to look at is our tangent of 2 theta. So the tangent of 2 theta is equal to the tangent of theta plus theta, which is the tangent of the first plus the tangent of the second, divided by 1 minus tangent of the first times the tangent of the second. So we end up with 2 tangent theta over 1 minus tangent squared theta. So the tangent of twice an angle is equal to 2 tangent of the angle divided by 1 minus tangent squared. And these are what we call our double angle identity. And we can use them in several different ways, and so that's what we'll do. Now, one of the ways we don't use them is to find exact values for angles that we didn't know. Because if we take the angles that we know 30 degrees. Well, 2 times 30 degrees is 60 degrees, but we already know 60 degrees. We know 45 degrees. Well, 2 times 45 is 90. We already know that. 2 times 60 is 120. We already know that. And so when you take one of the angles that we know the exact values for and you double it, you get another angle that we already know. So we can't use them to find exact values for angles, but we can use them when we're given the function of an angle. Let's say we were told that the sine of angle A was equal to negative 3/5, and A was in quadrant 3. What we want to find out is, well, what's the sine of twice that angle? Well, we know that that's equal to 2 sine A cosine A. That's our double angle identity. Well, we know that the sine of A is negative 3/5. Now, we don't know the cosine A, but we can draw our triangle. If this is A, the sine is 3/5 and a Pythagorean triple, so this is a 3, 4, 5. We're in the third quadrant. So the cosine of A is 4/5. We're in the third quadrant, so it's negative. So we end up with a negative times a negative is a positive 24/25. Okay, if we were given that same piece of information and we wanted the cotangent of 2a. Well, we know that cotangent is the reciprocal of tangent. So tangent was 2 tangent over 1 minus tangent squared. So cotangent, well, let's just go ahead. This is 1 over tangent of 2a, which is 1 over 2 tangent A over 1 minus tangent squared A. So multiplying by the reciprocal, we get 1 minus tangent squared A over 2 tangent A. And now we can substitute in. So we would have 1 minus tangent. Now the tangent would be 3/4. We're in quadrant 3, so it's positive squared over 2 times 3/4. So we have 1 minus 9/16 over 6/4. We'll worry about. And this is one that I wouldn't try to get necessarily to get a common denominator in both the numerator and denominator. And we could have canceled right there. In fact, let's go back and go ahead and cancel. I think it'll be a little bit neater if we do. So multiplying this, we would get 3/2. Now in the numerator, we need to do our subtraction. So 1 is 16/16 minus 9/16, which would be over 3/2. Well, that would be 7/16, and dividing by 3/2 is the same as multiplying by 2/3. So we end up with 14, well, we can cancel here. Goes in there 8. So we end up with 7/24. So given a function of an angle, then we should be able to find the function of twice that angle. if we were given that the cosecant of t was the square root of 5 and t was in quadrant 2. Say we were asked to find the cosine of 2 theta. Now, for cosine, we had 3 different identities. One dealt with sine and cosine, one dealt only with cosine, and one dealt only with sine. Cosecant up here is the reciprocal of sine. So if the cosecant equals the square root of 5, then the sine of t is equal to 1 over the square root of 5. So since we have a choice of which function or which identity to use, we had 3 of them, let's use the one that deals only with sine. And then we don't have to take our triangle and draw the triangle and find the other sides. So this would be equal to 1 minus 2 sine squared t. So we have 1 minus 2. Now the sine of t is 1 over the square root of 5 squared, which 1 squared is 1, square root of 5 squared is 5. So we have 1 minus 2 fifths. Well, 1 is 5 fifths minus 2 fifths would give us 3 fifths. And we could have drawn the triangle with the cosecant and then used any of our identities. We would get the same thing. But if we were going to use the 2 cosine squared theta minus 1, then we would have to draw our triangle so that we could get our other side and use it. But that's the nice thing about cosine, is you can use the one that's going to be the easiest for you. Okay, now we can also use this to do some simplifying. Let's say we were given that the cosine of 120 degrees was equal to the cosine squared 60 minus sine squared 60. And we wanted to actually evaluate it. We're going to use the exact values just to show that this is true, because this is our double angle identity. 120 is 2 times 60, which would be cosine squared minus sine squared. So this is the identity. What we want to do is prove that it's true. Well, for 120, our reference angle is 60. We rotate it around 120 degrees, so the angle between the terminal side and the x-axis would be 60 degrees. So the cosine of 60 is 1/2. We're in the second quadrant, so it's negative. Now, the cosine of 60 is 1/2, first quadrant, positive. The sine of 60 is the square root of 3 over 2, first quadrant, positive. We want to show that these are equal. Well, if we take this side, if we square this, we get 1/4 minus square root of 3 squared is 3, 2 squared is 4, so we get negative 2/4, which is negative 1/2. So yes, they are equal to each other. So you can do this with some of the angles just to show that they are equal. And we can also use it to simplify. Let's say that we were told that 2 cosine squared of 105 minus 1. And we want to evaluate this. We want to simplify it to see what it's equal to. Well, if you notice, this is in the form of our double angle identity for cosine. The cosine of 2 theta is equal to 2 cosine squared theta minus 1. So as we look at this one, this is 2 cosine squared theta minus 1. So this is equal to the cosine of 2 theta, and for this problem, theta is 105 degrees. So this is the cosine of 210, and 210 is one of our special angles. If we rotate it around, it's 30 degrees back to the x-axis. Cosine of 30 is square root of 3 over 2. We're in the third quadrant, so this would be negative. So we're looking for ways that we can take something and then write it as our double angle. Another one like that. The sine of pi over 8 cosine pi over 8. We want to evaluate this. Well, if this had had a 2 out here, and I'm going to just put it there. If that had had a 2 out there, that would have then been equal to the sine of 2 times theta, and our theta is pi over 8. But it wasn't, the 2 wasn't out there, but so if I take this now and divide both sides by 2, what I'm going to have is that the sine of pi over 8 cosine pi over 8 is equal to 1/2, dividing both sides by 2, the sine of 2 times pi over 8. So that would be 1/2 the sine of pi over 4. Well, I know the sine of pi over 4, that's the square root of 2 over 2, times 1/2 would be the square root of 2 over 4. And so again, by plugging it into our identities, we were able then to evaluate it. But we did have to do a little something here that was pretty creative. We didn't have the identity that we wanted. We had sine cosine. Well, looking back at ours, we have a sine cosine, but then it's times 2. So since that's not what we had, we couldn't just substitute in for it. But if I, multiply both sides, or do the opposite in that case, uh, twice this would be equal to this, and so dividing both sides by 1/2, then I was able to evaluate my function. Okay, we can also use this to prove some identities. And again, we're not going, it's not as involved as some of the identities that we had in an earlier section, but we will have to use some of our other identities. So let's look at a few of these. Say that we want to show that the cotangent of theta is equal to the sine of 2 theta over 1 minus cosine squared theta. Okay, now if we took our calculator and we put cotangent theta in y sub 1 and sine of 2 theta over 1 minus cosine squared theta in y sub 2 and graphed them, we would find that the graphs were on top of each other. In this case, we know that because we're already being told to prove the identity. And so we were told that it was an identity. We didn't have to decide. If we're not told that it's an identity, then you might have to do that first and then prove the ones that were identities. So we want to see if we can prove that this is equal. So if we do our identity, I think we would all agree that this would be the more complicated side. So let's just expand it. The sine of 2 theta is equal to 2 sine theta cosine theta over 1 minus cosine squared theta. Now, And that wasn't supposed to be a squared up here. I just looked and I wrote it in there incorrectly. This isn't cosine squared. This is cosine of 2 theta. So now what I'm going to do is substitute in for my cosine of 2 theta. And I have choices. And I think any of the choices that you make there for the cosine of 2 theta would probably lead you to the right conclusion. But I'm going to be thinking, I think that well, let's just try the 1 minus 2 sine squared theta. Okay, we would have 2 sine theta cosine theta over 1 minus 1 plus 2 sine squared theta. So those subtract out. So we have 2 sine theta cosine theta over 2 sine squared theta. Well, our 2's cancel. One of our sines cancels with one of those, and we have cosine over sine, which is cotangent. Whoops, should put that below there. Cotangent theta. And that's what we were wanting to prove that it was. So most of the time on these identities, just by substituting in, it's going to give you you're going to be able to prove the identity. Let's look at another one. 2 cosecant theta, cosecant 2 theta, I keep leaving off my 2, is equal to tangent theta plus cotangent theta. Now most of the time it's going to be easier to work with our identity that deals with our double angle part. So that's what I'm going to do. I'm going to leave my line out just so that I have a little bit more room. But if I work with this, cosecant is the reciprocal of sine. So this would be 2 times 1 over the sine of 2 theta, which is 2 times 1 over 2 sine theta cosine theta. My 2's would cancel, and I have 1 over sine theta cosine theta. Now, that's nice, except that's not what I wanted. I need tangent plus cotangent. Now, tangent sine over cosine, and cotangent is cosine over sine. So I'm needing some sines and cosines in my numerator. Well, I've got a 1. 1 is equal to a lot of things, but it's also equal to sine squared plus cosine squared over sine theta cosine theta. And now I can use my distributive property, and I can break this into 2 separate parts. So I have sine squared theta over sine theta cosine theta plus cosine squared theta over sine theta cosine theta. One of my sines cancels with this, and I have sine over cosine, which is tangent. One of my cosines cancels with this one. I have cosine over sine, which is cotangent. And so I was able to verify my identity. Now we could have values where we need to come up with identities for higher angles, maybe the cosine of 3 theta or the cosine of 4 theta. And you would do it in a very similar way. If you wanted 3 theta, then that could be the cosine of theta plus 2 theta. And we could go through there. But let's look at where we want the cosine of 4a. And we want to show that this is equal to the cosine to the fourth of a minus 6 cosine squared sine squared plus sine to the fourth a. Well, if we work with this, this is the cosine of 2 times 2a. Okay. Now, I think that probably this is the more complicated side, so let's go back and work on it. We might could get it from the other, but I think we could get it from here just as easily. Well, I'm still going to go back. So this is the cosine of 2 times 2a. Sometimes I change my mind. So we can think of 2a as being our theta. Now we have several identities to deal with the cosine of twice an angle. But since I want to end up with sines and cosines, I'm going to use the one, well, that it's cosine squared of whatever my angle is, 2a, minus sine squared of 2a. And then I can take 2a here, and I can apply my identity for it. So cosine of 2a, that can be the cosine squared of a minus sine squared of a, and then this whole thing is squared, minus, for sine, we know that sine is 2 sine a cosine a squared. Okay, if I work this out, if I write down cosine squared minus sine squared times cosine squared minus sine squared and use my distributive property, what I'm going to get is cosine to the fourth a minus 2 cosine squared a sine squared a plus sine to the fourth of a. Okay, then minus, well, if I square this, this is all one term, so that would be 4 sine squared a cosine squared a. Now, looking at like terms, I've got some right here. I've got a cosine squared sine squared cosine squared. So I end up with cosine to the fourth a minus 6 sine squared a cosine squared a plus sine to the fourth of a. And so I've gone through and proven that identity by taking twice a double angle. And there can be other ways of doing this. Remember, in your proofs, it's not just one way. Okay, so these are your double angle identities, and normally we use them for simplifying, for making something more complicated easier, or if we're given the function of an angle, then being able to find a function of twice that angle.